Alright, in this video we take up the process of discharging a capacitor. So if you watch the previous videos, you know that we have a capacitor here and we've charged it up using a battery or some power supply, and it has some voltage. Right now, let's say that it's 10 volts. And then what's going to happen is that charge capacitor has energy stored in it. And that energy can act just like a battery can act. Use that energy to pump charge to other things. Now right now it's not able to do that because this switch is open and therefore there is no current flow. That means the charge cannot leave this capacitor and go over and be attracted to the negative charge on the other side of the plate. So right now there is no current flowing in this circuit. 0 amps. Furthermore, since there is no current flowing through here, there is no voltage dropped across the resistor, 0 volts. But there is some voltage, whatever that is, right now across that capacitor, and that means that as I go around this circuit, that voltage has to be dropped somewhere. It's dropped across this switch. So right now that would be 10 volts, for instance, if that's what my capacitor was charged to. So again, the open switch is where you can get shocked. Let me put in those results into our notes. Current flowing through the circuit, open circuit, no current flows through it. Follow our same symbols we used before. That means the current at time 0, but the minus means just before the switch was closed. 0 amps. Ohm's law says the voltage across the resistor is equal to the current across the resistor times its resistance, but there was no current through the resistor, so therefore there were 0 volts across the resistor. The charge on the plates of the capacitor, we were told it was Q naught. And if you know the capacitance and the charge, then you know the voltage across the capacitor. Because it's the charge on the plates divided by the capacitance. Alright, now we shut the switch. Now when we shut the switch, the voltage in the switch becomes 0. That's because every point on the switch here becomes an equipotential surface. So Vs is 0 volts. The switch is shorted. The capacitor positive charges see those negative charges and begin to want to be attracted to them, and they begin to flow around. And as they do, the charge on the plates will go down, and the voltage between the plates will go down. The electric field between the plates will go down, and the energy stored in the capacitor will go down. And we say that the capacitor is being discharged. That energy that was initially stored in the capacitor will be spent, dissipated, by this resistor. And in the end, there will be no energy left in this circuit. Well, we need to find the voltage across this resistor, and we can do that if we know the voltage across this capacitor. So here's how we analyze the circuit. First, the charge on the plates of the capacitor can never instantaneously change. So the charge now is the same as it was before. The voltage across the capacitor can never instantaneously change. So the voltage across the capacitor is the same as it was before the switch was thrown. Now what about the voltage across the resistor? The voltage from this point to that point is the voltage across the capacitor. But the voltage from this point to this point is also the voltage across the resistor. Therefore, the resistor is in parallel to the capacitor. It has the same voltage. Well, we know the voltage to the capacitor, so therefore we know the voltage to the resistor. Now we can find the current through the resistor using Ohm's law. The current is equal to the voltage in the resistor over the resistance, which is just VCO, divided by R, which of course, if you want, is Q over RC. By the way, that's Q naught over tau. So we found all of the values, and we didn't use any advanced math, just by looking at definitions of parallel, series, short, open, so forth. Using Ohm's law, using the definition of capacitance. We didn't do any advanced mathematics. Now we're going to find out what's going to happen after it's been running for a long time. Well, if it's been running for a long time, all of these positive Q's will eventually go over here, be attracted to these minus Q's. When you add a positive Q naught to this side, negative Q plus positive Q equals 0. And when you take a positive Q from the top plate, you'll end up with no charge. So there'll be no charge on the plates. When there's no charge on the plates, there'll be no voltage across the capacitor. When there's no voltage in the capacitor, there's no energy stored in the capacitor. When there's no energy stored, the capacitor will not be able to drive the current anymore. So there'll be no current flowing in the circuit. In short, the circuit will have used up its energy and will be stationary. Will not be doing anything. Well, that's all we need to do to put in all of our values. The current goes to 0. The voltage across the capacitor goes to 0. The voltage across the resistor goes to 0. Must have missed something at the top. Let's see. Current flows. Oh, this asked me what was the charge. My fault. Alright. No charge. And the last one, which should say I infinity, will equal 0 amps. Everything will go to 0. Let's go and fill up our graphs with our results now. So in our graph, we originally had a charge Q, and then it went down to 0. So it went down like, and it originally had some voltage Q naught over C, and it went to 0. Again, as you talked about in the previous videos, this graph here and that graph there must look alike by the definition of capacitance. So there was voltage on the capacitor before the switch was closed. There was charge on the plates. We plugged it in. We closed the switch, and it exponentially decayed. In terms of the current, there was no current. Let me change the pins here a little bit. There was no current. All of a sudden the current jumped up, and it jumped up to whatever that voltage was, divided by the resistance, and then it went down, and the voltage jumped up. Not a very good drawing, sorry about that. And then it went down. So the graphs look the same here, except that there's not a discontinuity in the charge and voltage like there is in the resistor. Those results are actually listed over here. And you see they each have an e to the minus t over tau. And that tau is still RC. Now, you need to be careful. The time constant in a charging circuit and a discharging circuit may not be the same if they've changed the resistors through which it charges to what it discharges. Another important thing. If you work with televisions or any other type of electrical thing and you have large capacitors, you need to be careful. These capacitors look like cans, and if they have a physical size comparable to your hand, they may have enough energy to vaporize a screwdriver and kill you. There is a circuit that when you unplug the TV or such is supposed to constantly bleed off this charge over some time so as to protect you. But if that circuit gets broke, and if you've unplugged the television set, it doesn't matter. If this circuit is broke, this charge and this voltage stays on this capacitor with its energy. And I said that energy is enough to vaporize a screwdriver. Even with the TV unplugged, if you touch one of these capacitors and you don't know what you're doing, you potentially could kill yourself. I wouldn't guess and hope my life that this circuit is working properly and isn't faulty if I'm working on the back of a TV. People who work with them know what they're doing. An electrical engineer or physicist knows how to short the capacitor in a safe way to guarantee that it has no energy so that they can work on it. If you don't know what you're doing, keep your hands off of the cans. It's a very famous saying for people to protect themselves when working with electrical circuits. Okay, in the next video we'll show you how to actually do some of these calculations on a sample problem. I'll see you then.